Okay, so in the previous lesson, we derived the work energy theorem in its general form, and right now I'd like to talk about what exactly the work, how it is defined in two or three dimensions. So if you recall, at a certain point in the derivation, we found that 1/2 m times the derivative with respect to time of the velocity j squared is equal to the infinitesimal work done, and that is equivalent to f of rj dot product delta rj. Okay, so essentially we were analyzing the forces acting on a particle at a particular segment of its trajectory. Okay, so if you look at the particle, here are our two axes, and I'll draw the trajectory. So right here we have our trajectory C, okay, C, and say that we take a random point, okay, here, right here, which has position vector r, and then we take a point close to it, which will be r plus delta r. And well, what is the delta r vector that we're using in our expression? It's this vector right here. It's the vector tangent to the path C at this point here, okay? And here we're obviously taking the limit as delta r approaches 0. Okay, we want to consider an infinitesimal segment, a very small segment. Okay, so let's say that the force acting on the particle at that point is here, it's f of r, and we should actually say f of rj because we're considering the segment j. Okay, so this will be rj, this will be rj, this will be delta rj, and this will be delta rj. Okay, so we're considering a segment with index j, segment j. Okay, infinitesimal. So what is this dot product right here? Well, it's simply taking the component of the force along the direction delta rj. Okay, so this right here, this component right here, is the dot product that we are looking for. It is f of rj, so f of j dot product delta rj. And what we're going to do now in our derivation, as we saw, was sum over all of these infinitesimal segments. So from j equals 1 to n. Okay, so let's say we divide it into n segments of m d dt of vj squared. Oops, here I forgot a delta tj, sorry about that. Delta tj equals the sum, again, over all of these segments of f of rj dot product delta rj. Now we take, as we said before, the limit as tj approaches 0, which means that n approaches infinity. So we're going to take an infinite amount of infinitesimal segments along the path C. Okay, so consider just all of these delta r vectors, okay, and we take the component of the force acting at those points in the direction of these delta r j vectors. Okay, we're going to sum all of the components of the forces along these vectors I just draw, and that is the work done on the system by the force F. Okay, so we're going to take this sum with this limit right here, which essentially means taking the integral. Okay, so we're going to have the integral. Let's say that this starting point is ta time ta, and this ending point is time tb. I'm going to integrate from ta to tb of d dt v squared dt, and that is equal to the integral of f of r dot product dr. Okay, and we're going to do this along the path C. Okay, and we saw this checked out, we expanded this into, we solved this integral, and we found the work energy theorem from it. So this here we said was the work done by F, and I repeat, it's like taking all of these components for each of these infinitesimal line segments and summing them all over along the path C. That is the work done. So hopefully that cleared up a bit of the conceptual aspect of a line integral, more specifically the line integral of the force, which is equal to the work done. And I'd like to finish with a small remark, because if you look at it closely, you see, hey, but here we're integrating along that path C, and that path C is a trajectory of the particle, right? And we're using the work energy theorem, to find the trajectory C, right? However, to use the work energy theorem, we need to know C, right? That makes sense. It's right here in the formula. We need to know the trajectory of the particle. So this is a paradox. Like, you need to know the solution to apply the formula, but that doesn't really make sense, right? And luckily, for very special forces, which physicists call conservative forces, this last statement, that to use the work energy theorem we need to know the trajectory, is false. Okay, so false for conservative forces. And that is very good, because that means that this formula that we derived is actually going to be useful, and we can solve it. We can solve problems with it. Alright, so hopefully that was helpful.